Hey everyone. In this video, we're going to be looking at the reactions of alcohols, aldehydes, ketones, and thiols. So let's start with the reactions of alcohols, particularly how to form alcohols. Now, we learned this reaction in chapter 11. This is the hydration reaction, in which you take an alkene, you react it with water using an acid catalyst, and the water splits apart as H and OH, and one half of it adds to one of the carbons as H, and the other half of the water adds to the other carbon as OH. And where the double bond used to be is now a single bond. And we have now formed an alcohol because we have an OH group attached to the molecule. So we turn an alkene into an alcohol using hydration, adding water. Okay. Well, it's actually possible to do the reverse of the reaction as well, but the reverse requires some heating. Now, if adding water is called hydration, then removing water is called dehydration, right? You're dehydrating the molecule. So you take your alcohol, you treat it with acid and heat, and you will remove the H and the OH from the molecule, and they will recombine as water, leaving you the alkene. So the dehydration of an alcohol forms an alkene, right? Same reaction, just opposite direction. Now, asymmetrical alcohols run into the issue of potentially forming two products. So let's consider this. Here's a molecule with an alcohol, and it's not symmetrical. The right side has a CH3, the left side has a CH2, and then another CH3. So that's different on each side. Now, in order to do the dehydration, we have to remove an H and an OH. And so let's say on the left here, we remove this hydrogen and the OH to make H2O. Well, if you remove this hydrogen and this OH, you're going to end up with a double bond between those two carbons right there. And so that's how we form this double bond. Alternatively, you can remove a different hydrogen. So what if I remove this hydrogen and the alcohol to form water? Well, now the double bond is going to be here between those two positions. And so how do we know which is which? Well, as it turns out, there is something called Zaitsev's rule, which tells us that the major product is always the one that has the most alkyl groups bonded to the CC double bond, or the most carbons attached to the CC double bond. So going back here, if we were to look at the number of carbons connected to the double bond, we have one carbon on this side and another carbon on that side. So two carbons attached to the alkene. Now the molecule on the right, we only have one bond to a carbon. The other side is both hydrogens. And so another way you could think of this is like a primary alkene versus a secondary alkene, right? The more carbons you have attached to the double bond, the more stable it is. And so the major product is always going to be the one that has more carbons attached to the double bond. And the one that had fewer carbons attached to the double bond is the minor product or the byproduct of the reaction. So let's do a study check. Predict the major product of the following dehydration reaction. So this is Typical question you'll get on the exam, right? We see that it's an alcohol. We're adding acid. Remember, H plus is the abbreviation for an acid, and heat. And so we're going to be removing H and OH. And so now we have to ask ourselves, where are the hydrogens that are going to get removed? So let's draw these in. We know that there's one hydrogen here, and then two hydrogens on this position. And so we have to remove one of these hydrogens and the OH. And so let's color coordinate it again. If I remove this hydrogen here in red to make my H2O, my molecule, my alkene molecule that I formed would have the double bond here between the H and the OH that I just removed. Alternatively, if we removed this hydrogen on the other side, that I'm showing in blue, our product would have the double bond over here. And we want to figure out which of these is the major and which is the minor product. And so we need to look at the number of carbons attached to the alkene. And so looking at both positions on the alkene, I see one bond to a carbon, two bonds to a carbon. So this would be like a secondary alkene, if you will. Now, in red, looking at the two carbons of the alkene, I see one bond to carbon, two bonds to carbon, and three bonds to carbon. And so because the red one has more carbons attached to the alkene, it's more favored. And so this would be the major product, and the blue would be the minor product. So once again, if you have an asymmetrical alcohol, where it's different on both sides, the major product is always the one that has more carbons bonded to the alkene. Next reaction we're going to talk about is oxidation and reduction. And so this is what we did in lab last week, or earlier this week, I guess. And so oxidation refers to the number of bonds to oxygen that a carbon has. And reduction refers to reducing the number of bonds to oxygen. And so here are 5 different carbon compounds showing varying states of oxidation. On the far left, we have the fully reduced form of carbon. And on the far right side, we have the most oxidized form of carbon possible. 4 bonds to oxygen, carbon dioxide. And then we have 3 bonds to oxygen, which is a carboxylic acid. 2 bonds to oxygen, which is an aldehyde or a ketone. And then 1 bond to oxygen is an alcohol. And no bonds to oxygen is an alkane or a hydrocarbon. Now, the number of bonds to hydrogen increases as you become reduced, right? So this is CH4 with 4 CH bonds, 3 CH bonds, 2 CH bonds, 1 CH bond, and no CH bonds. So reduction is increasing hydrogens, and oxidation is increasing bonds to oxygen. So let's talk about the oxidation of alcohols. Here, I have 3 examples. I have a primary alcohol, a secondary alcohol, and a tertiary alcohol. Let's look at what happens to each one when we try to oxidize them. So the symbol for oxidation is brackets with an O. That means oxidation. And currently, this carbon only has one bond to oxygen. So if we oxidize it, it's going to end up with two bonds to oxygen. Everything else stays the same. And so every time you oxidize, you have a loss of hydrogens. Specifically, we're losing the one on the OH and one of the ones from the carbon. And so those two hydrogens leave, and the carbon forms the double bond to the oxygen. But this can get oxidized one step further if you react it again. And two bonds to oxygen would become three bonds to oxygen in the form of a carboxylic acid. So a primary alcohol always oxidizes to become an aldehyde, and aldehydes always oxidize to become carboxylic acids. Just like we saw on the chart here, alcohol becomes the carbonyl, becomes the carboxylic acid. All right, let's take a look at what happens to a secondary alcohol. So in order to oxidize it, we need to be able to remove hydrogens. Well, we're going to remove this one, and we're going to have a loss of hydrogens. And where the carbon-oxygen single bond was, we're now going to have a double bond. Everything else stays the same. Okay. So 3 carbons, then the carbonyl, and then 2 carbons. So 3 carbons, carbonyl, 2 carbons. We lost hydrogens, and we increased the number of bonds to oxygen from 1 to 2. So the secondary alcohol becomes the ketone. Okay. And if you try to oxidize a ketone any further, it does not work. You would get no reaction. Ketones are much more stable than aldehydes, and so ketones don't oxidize any further. Now, for tertiary, it's a little different. So remember when we oxidized, we were ripping off hydrogens? Notice there's no hydrogen on the carbon here. Because there's no hydrogen to be removed off this carbon, oxidation does not happen. So you would get no reaction if you tried to oxidize a tertiary alcohol. They just don't oxidize. And it's because they don't have any hydrogens on the carbon to be removed, okay? Unlike primary and secondary alcohols. All right, let's do some practice here. Predict the products of the following oxidation reactions. So oxidation is increasing the number of bonds to oxygen. We currently have a single bond to OH. And so if we oxidize it, we should end up with a double bond to the OH. All right. Single bond becomes a double bond. We're always increasing the number of bonds to oxygen when we're doing oxidation. All right, now this one here, there's our bond to oxygen. So we're going to turn that into a double bond. And we could leave it just like that, or we could be nice and throw in the extra hydrogen there to emphasize that, yes, indeed, it's an aldehyde. And if we were to fill in the skeleton structure initially, there are 2 hydrogens there. Technically, only one of them has to get removed. We remove that one and that one. And the one that remains is the one that we drew in here on the aldehyde. So you don't have to show it. You could leave it hanging, if you will. That's totally fine, but I tend to draw them in on exams. All right, let's talk about reduction, the opposite of oxidation. So reduction implies the addition of CH bonds. So we're adding hydrogens back into our molecule. And where are we going to add them? Where the double bond is. So we're going to break the double bond here, and we're going to be adding H. So if I was to redraw that, this would be an OH. And the hydrogens would be back. Okay. So reduction is reducing the multiple bonds to oxygen to a single bond oxygen. Same concept with a ketone here. Double bond O, we're going to add our two hydrogens, and the double bond becomes a single bond once again. So 1, 2, 3, 4, 5, and that's just going to be OH. And that's it. So oxidation, you increase the bonds to oxygen. Reduction, you reduce the number of bonds to oxygen by adding hydrogens. Okay, can we predict the products of the following reactions? So this looks like an aldehyde to me. And it looks like we're adding hydrogen gas back in. So we're going to get two hydrogens added in where the double bond used to be. Everything else stays the same. The ring is unaffected. And then we would have two new hydrogens attached where the double bond used to be. And so we went back to the primary alcohol. All right, now for the next one, looks like a ketone, but it's going to be the same reaction scheme, right? Wherever the double bond is, that's going to break, and you're going to end up with a hydrogen on each side of that double bond, which is being turned into a single bond. Whoops, excuse me. So reduction, we are adding the two hydrogens back onto the molecule. Now, let's talk about the oxidation of thiols. So thiols behave a little differently. When we oxidize, we're removing hydrogens, and that is true for thiols as well. So when we oxidize these, we're going to be removing the two hydrogens, and we're going to be connecting the sulfurs together. This is known as a disulfide functional group. So two thiols, when they're oxidized, you rip out the hydrogens and you connect the sulfurs together. This reaction will become important when we start looking at proteins later on. So keep this in your mind because you'll see it again. Actually, you'll see all these again. So let's do a practice here. Predict the products of the following oxidation reaction. Well, this looks like a thiol. This looks like a thiol as well. And so I am going to be removing the hydrogens and connecting the two sulfurs together. just like that. So copy, copy, paste them together, but without the hydrogens, and the sulfurs are connected. So that's the oxidation of a thiol. And that's the last reaction we have to talk about for chapter 12. So once again, to recap, you form an alcohol by hydrating an alkene. You remove an alcohol by dehydrating it to reform the alkene. And the dehydration forms the major product, which has more carbons attached to the alkene. And then oxidation means the addition of bonds to oxygen. Reduction means reducing the amount of oxygen or increasing the amount of hydrogen. And if you oxidize thiols, you are connecting two sulfurs together as a disulfide. Okay. Thanks for watching, and I'll see you in the next set of videos.